Hi, grade 12. Today we're going to be looking at acids and bases. We're going to start with looking at the theories around acids and bases, basically how we define what an acid is and what a base is. So we have two theories, but now we'll be looking at Arrhenius' theory on what an acid is and what a base is. Arrhenius says that a base is a substance which produces hydrogen whenever in solution, right? So Arrhenius classified his acids and bases according to the formula and how they behave with water. That's the part solution. So it says when it's in solution, when you dissolve it in water, it will produce hydrogen. And with regards to bases, he says that when they are in solution, they are going to produce hydroxide. We have an example here of hydrochloric acid in water to produce hydronium. In this case, hydronium is seen as just a proton. So the hydrochloric acid released that proton, thus it meets the definition for Arrhenius. Then we get to our base. You can see here sodium is going to dissociate in water to form sodium and hydroxide. This is sodium hydroxide, dissociating. This is ionization. This is deassociation. So there's a difference between this reaction and that. This is acid reacting with water, ionization, and this is the base reacting in water to form sodium and hydroxide. The problem with Arrhenius' definition is that it is limited. So the limitation for Arrhenius comes in because some substances do not discrete hydroxide ions, but are still considered bases. For example, ammonia is a base, although when it's in water, it does not release hydroxide. We have sodium carbonate, also a base, but when it's in water, it's not going to then release any hydroxide. We also have another theory. This is now from Laurie Bronsted. This theory from Laurie Bronsted is much better than the Arrhenius one because it includes all of our bases and it also includes all of our acids. So let's look at the definition with regards to the Bronsted theory. He says that an acid is a proton donor and that a base is a proton acceptor. So the ability to accept a proton, a hydrogen ion, or to donate a hydrogen ion is what makes a base and an acid. Here we have an example where we have hydrochloric acid, and the water in this case is going to act as a base. The hydrochloric acid is going to donate the hydrogen ion, and the water is going to then accept the hydrogen ion. So we can see that this is a base because it accepts, and that's an acid because it donates. Here we have ammonia reacting with water. So this is one of the bases that ionizes instead of dissociating. So it will ionize in water. We can see how the acid in this case will be our water. Our water is going to release a hydrogen to ammonia. Then we have ammonium ion over here and a hydroxide. The water is the acid because of its ability to donate a proton, and the ammonia is then a base because of its ability to accept a proton. So when it comes to acids, we have monoprotic and diprotic acids. Let's take a look at these definitions to see what we mean by that. So monoprotic acids are acids that are only able to donate one proton whenever they are in water or they are reacting with a base, they will be able to only ionize and donate one proton, whereas diprotic implies that they're able to donate more than one hydrogen or one proton. In this case, we can see that sulfuric acid has the ability to donate two hydrogens instead of just one. The next thing we're going to look at is how do we identify a strong base and a strong acid. So we talked about how an acid is going to ionize in water. So here is our acid ionizing in water to form hydronium and a negative element or a negative ion in this case. So if we wanted to calculate the ionization constant of our acid, we will say then remember that the constant only takes in either gas or aqueous solutions. So in this case, it will only be the concentration of our hydronium, the concentration of our negative ion, and the concentration of our acid. We won't put in the concentration of water because water has an infinite concentration. We cannot in any way compute that. Okay? So to calculate the Ka value, we would see that we are going to have our product of this ionization over our reactants. And if you put your ions, let's say in water, if you put your acid in water and it ionizes completely, right, or let's say up to 99%. If you put 10 grams of sulfuric acid in here and all that sulfuric acid turns into iron, we're saying completely, it means that we would have greater products at the end than we would have reactants. Right. And we can see that the Ka value is directly proportional to the concentration of our product. So if we have high concentrations of our product, we will have a high Ka value. Whereas if you use a weak acid and so when you put it in water, not all of it turns into iron. Let's say you had 10 grams and only about 1 gram of that turned into iron. The rest stayed as a molecule, as a compound together. Then we can say here that the relationship still holds because now the concentration of our products at the end is low. We would have a low Ka value. So a low Ka value tells us that this is a weak acid, and a high Ka value tells us that this is then a strong acid. So we also have a similar thing for Kb. Or in this case, let's say for our base. For our base, we have what we call the dissociation / base constant. So let's go ahead and take a look at that. The Ka value is similar to the Kb value in terms of how we calculate it, right? So we can see from the equation itself, we have the salt, the hydroxide, and over our base. We do not include water because water has infinite concentration. Okay. So in this case, we can see that for us to have a great Kb, we need to have more products than we have reactants. This implies that when we then add our base to the water, if it dissociates, most of our bases are going to dissociate as only, I think, ammonia and sodium carbonate, mostly that's going to ionize. right? So if it dissociates and or ionize in water, we would form more of our salt and our hydroxide, right? So a strong base is going to fully dissociate in water, thus giving us a high value for our, or the concentration for our product would be low, therefore, high, therefore, we expect a high Kb value. Whereas for weak acids, we then expect a low Kb value. Okay. Now, it is your responsibility to have a list of weak acids and also strong acids. It's your own responsibility there. Okay, so the next thing we're going to do is looking at the conjugate ace and base pairs that we have. So in our chemical reaction, we're going to have a base that has no hydrogen reacting with an acid that has a hydrogen. Now, what they're going to do is that the hydrogen is going to be given to the base, and now the acid is just a negative ion. In this case, if we look at it from this perspective, right, because this is going to be a two-way street, right, it is reversible. So because it's reversible, it means that your reactants, your products are able to produce your reactants. In this case, this is going to act as our acid because it has a proton that it can donate. This is going to act as our base because it is able to accept a proton. Now let's look at this example of ethanoic acid reacting with water to produce hydronium and our ethanoate ion. Right, so here we have our acid giving the base. This is our base for our forward reaction, giving the base a hydrogen. Now, when the acid gives the base the hydrogen, it now becomes a base because it's able to accept a proton, right? Also, in terms of our reversible reactions, we know that that negative ion can actually go back and form your ethanoate, your acid again, right? And for the reverse reaction, our hydronium has an extra proton to give off, so now it becomes the acid. And because it can donate back, we do have our base being formed on this side. So this is our conjugate base pair and acid. This is a conjugate base to that acid, and that acid is a conjugate acid to that base. The next thing we're going to be looking at is amphoprotic substances. Amphoprotic substances are substances that can act as a base or an acid depending on what they act with. So here we have water, so can act as a base or acid. Here we have ammonia reacting with water, where in this case water is the acid, and it's going to give off its extra hydrogen to ammonia to form ammonium, and ammonium now is a base because it has a high extra hydrogen that it can give off, or in terms of the reverse reaction, ammonia is going to act as a base because of that extra hydrogen that it has. Our water, after giving up its hydrogen, there we can see it behaving as a base because at this point it can accept a proton. Right, so that those two are conjugate pairs, and these two also, those ammonia and ammonium conjugate pairs, water and hydroxide conjugate base pairs. Now, let's look at it acting now as a base. We have it reacting with an acid, right? So in this case, it's going to accept the proton and become the conjugate acid. And the arsenic acid would then lose the hydrogen and it will act as a base. So we can see that water can act as a base or an acid. It's all dependent on the other reactant. In example 2, we have sulfuric acid. Now, sulfuric acid itself is not the amphotic substance in this case, but our hydrogen sulfate ion is. So in this case, sulfuric acid is reacting with water to give us hydronium and a hydrogen sulfate ion. So it gave off one of its hydrogens. It is acting as a conjugate base, but that conjugate base can also act again as an acid reacting with water to form sulfate and hydronium. So we can see here it's acting as a conjugate base and there it's acting as an acid. So it has the capability to act both as an acid and as a base. So let us now go into the reactions that we have with regards to our acids and base. The first one that we're going to look at is neutralization. And we're going to look at neutralization. This is when an acid acts with a base. And we want to determine mostly what will be not only what would be our end result, but we also want to determine if the end result is going to be acidic or basic. So a neutralization reaction takes place when an acid reacts with a base in aqueous solutions to form salt and water. So there is our acid, there is our base, and we're going to form salt. Salt is the product of a metal and a nonmetal. That will always be our salt. They go through ionization. They are ions. They are produced from ions. I forgot. I know for the I know for the nonmetals, it's called the covalent bond. This is called a. Okay, and I'm gonna leave it up to you to call it. My mind just went blank. I forgot, but we do this in grade 10, and we are also producing water over there. So let us look at the different reactions that we can have. Okay. So whenever we are reacting a base with an acid, we have what we call the equivalence point or the end point of our reaction. The equivalence point just means that I have reacted geometrically equivalent amount of our base and our acid, meaning that geometrically implies I'm following the relationship that's given to me in the equation. So in this equation, they say 1 mole of hydrochloric acid will react with 1 mole of sodium hydroxide. Right. So if I have balanced out those, then I get to an endpoint. As soon as one of either the acid or the base is in completion, then the other one needs to react equivalently, and that would be in completion. So that would be then my endpoint. So if I react a strong acid with a strong base, I am expecting the solution at the end to be neutral. So a strong acid with a strong base would then give me a neutral solution. So this is just an overview. A reaction of weak acids with a strong base. So if I have a weak acid and a strong base, I'm expecting the overall solution to be alkaline or basic. If I have a strong acid with a weak base, I expect that the overall reaction is going to be acidic, meaning this solution that I get at the end. That product should be acidic. That product should be basic. Now, the way they will test you is that they would expect for you to do a hydrolysis reaction of the product that you get so that you're able to determine whether something is going to be, a solution is going to be acidic or basic. So what we're going to do is we're going to look at the steps that you need to take to see if something is acidic or basic, or your end result is acidic or basic. Once we're done with that, we're going to go ahead and look at an example as to how we go about that. The first thing we're going to do is we're going to split the salt into its ions and decide from which acid and which base the ions are coming from. For example, if your salt was sodium chloride, you would say, oh, this is coming from hydrochloric acid, and this is coming from sodium hydroxide. Right. Then we're going to determine whether each of the acid or the base is a weak or a strong one. If an ion comes from either a strong base or a strong acid, it will not undergo hydrolysis. So this is in this case, it doesn't help us a lot because both of them are coming from strong base and strong acid. So it means both the sodium and the chlorine are not going to go through hydrolysis. But say we had something that would go through hydrolysis. Let's say, okay, we have a salt. The salt is X and Y is coming from a strong base, and X over here is coming from a weak acid. The hydrolysis won't go through the strong base. The hydrolysis is going to happen to the weak acid part. So once we see which part is going to go through hydrolysis, we're now going to take that through hydrolysis. So once they've decided which one, either the positive or the negative, will undergo hydrolysis, we now need to write out an equation that's going to represent this hydrolysis that we have. So they've given us an example over here where our hydrogen carbonate is reacting with water, and the water gives its hydrogen to the hydrogen carbonate, and therefore we have hydrogen carbonate and hydroxide. Right. So the hydrogen carbonate is coming from a weak acid, and that's why we use it as a part. But you will see this when we do better examples to say, okay, why did they use this part in the reaction? Why did they use that part in the reaction? And whether you form hydroxide or you form hydronium, you would be able to determine whether it is basic or acidic. If you form hydronium during hydrolysis, then you know that your solution would be basic. And if you form if you form hydronium during your hydrolysis, then you know that this is going to be an acidic solution. So in example 1, we had a salt, ammonium chloride, and we wanted to know if ammonium chloride is going to be basic or acidic. So we separate the ammonium ion and the chlorine, and we note that the ammonium comes from ammonia, and we note that the chlorine comes from hydrochloric acid. This is a strong base that is a weak acid. So that's a strong acid and that's a weak base. So the strong acid ion is not going to, what is left over, the ion is not going to go through hydrolysis. It's then the ammonium that's going to go through hydrolysis. So we have chosen here to say ammonium is the conjugate acid of a weak base and will go under hydrolysis. So here we have it reacting with water to form ammonium and ammonia and hydronium. So because we formed hydronium, it implies that the pH is going to be less than 7. So this solution here is going to be acidic. We go to example 2. We have sodium nitrate. We understand that the sodium comes from sodium hydroxide and the nitrate comes from nitric acid. Nitric acid is a strong acid, so that means it is the sodium that's going to go through, both are actually. So none of them will go through hydrolysis because it's coming from sodium hydroxide, which is a strong base, and nitric acid is also a strong acid. So none of them will go through hydrolysis, and our pH is going to be at 7. Here we have sodium hydrogen carbonate. And we understand that sodium comes from sodium hydroxide and hydrogen carbonate comes from carbonic acid. Carbonic acid is a weak acid, so therefore the hydrogen carbonate is going to go on a hydrolysis. It's going to react with water where it acts as a base and water acts as an acid, and it will give off its hydrogen. Therefore, it would form hydroxide, and because it forms hydroxide, we know that the pH is going to be less than 7, and that's going to give us a basic or an alkaline solution. So the next thing we're going to look at is titration. Titration is really important. I think most of the times my students get titration incorrect because of the basics that we were supposed to learn in grade 12, changing concentration into moles, changing moles into mass. So that's where the biggest problem comes in when it comes to titration. Okay. So the aim of titrations is to understand or to determine the concentration of an unknown acid or base, depending on that. The aim of titration is to determine the amount of acid in a solution by determining the volume of the base of the unknown concentration that will completely react with the known solution. Now, the known solution is called the standard solution. Okay. So while you're studying, take a look at what the experiment for titration looks like. You can go on YouTube and find a nice titration YouTube videos that tells you about the precautions that you need to take while doing this, what type of procedures you're going to use here. And the most important part about the titration part is being able to pick an indicator. Okay, so how do we pick an indicator? Let's take a look at some of the indicators that we have in the industry. We have the bromethyl blue, which works in a range of 6 to 7. So you would use this, because of its range, you would use this when you have a strong acid and a strong base, because you know that the equivalent point is going to be neutral around 7. So you want something that's in the 7 region. If you have a strong base and a weak acid, then you would use your phenolphthalein because its range is in the basic side, and we know that when we have a strong base, our end point is going to be found in the basic end. And when you have a strong acid and a weak base, you are going to then use metal orange because you can see the range that it works in. We know that whenever we have a strong acid, our overall solution at the end is going to become more acidic. So you would want to use something that can show you the endpoint when the solution is done. You don't have to note the change in color unless you're doing IV. So over here, we have a standard solution is prepared in a 200 centimeter cubometric flask by dissolving 4.9 grams of pure sulfuric acid in the water and filling the flask to the mark. During a titration, 20.7 centimeter cubes of the standard solution completely neutralize 10 centimeter cubes of a sodium hydroxide solution of an unknown concentration. So the first thing we're going to do is we're going to write the balanced equation. We have sulfuric acid reacting with sodium hydroxide, which will form a salt. The salt is going to be made up of a metal and a non-metal. So we're going to have sodium sulfate and also water. Let's balance the equation. I have 2 there. I need to have 2 over there. And my equation is balanced. That's step 1. For you, step 1 might be already done in your book, so that's great. We then move over to step 2, which is determining the concentration of your standard solution. Here they gave us the mass and they gave us the volume. So the concentration we would use the formula M is equals to the molar mass multiplied by the volume. The mass is 4.9. The molar mass of sulfuric acid would be 2 hydrogens plus sulfur. I believe sulfur is somewhere around 32. A good tip here would to always have whenever you're studying, whenever you're practicing something, is to always have your formula sheet ready and open, which is something I didn't do at this point. Very much disappointed. That's the one thing I always tell students to do. So let's just have it open again for ourselves so we can see. So always open yours. Make sure you have it open, especially when you are doing practice questions. So sulfur is definitely 32. So we'll have 32 there. And we have 4 of the oxygens, and oxygen is 16. And we want to multiply that with the volume that they used to form this one here. The volume is 200 centimeter cubes, but we know we do not work in centimeter cubes, we work in decimeter cubes. So we're going to have to divide that 200 by 1,000, and we're going to plug that into the calculator. We get 0.25 moles per decimeter cubed. Now we're going to then calculate the number of the concentration of our base using the equation. You know, that big equation in your textbook. I'll see if not in your textbook, but let's see if we have it in our data sheet. So I'm using the CAPS data sheet if you are following with me. Okay. There we have an equation that says Ca multiplied by Va over Cb multiplied by Cb is equals to Na over Nb. Because we are looking for the base, I would rather we invest all of this. So have it as Cb Vb over Cb Vb Nb V Nb. And in this case, we know the volume of the base. We know the volume of that's supposed to be A, sorry. We know the concentration of the acid. We know the volume of the acid. We know that we use 20.7. We know the moles. So the moles, these ones here are your stoichiometric ratios. So they are according to the formula. We know the value for your base. We know the value for your acid. So we're going to write that Cp should be equals to NB Ca Va over Vb Na. Our NB is the stoichiometric ratio of our base, which is 2. Our Ca is the volume of the acid, which is 20.7, but we work in decimeter cubes, so just divide that by 1,000. Oh, that's our volume. Sorry, the volume. The concentration is 0.25. Our Vb is 10. Again, write that in decimeter cubes. And the coefficient of our acid there is 1. So that's supposed to be Va. Vb, Na is the number of moles, so the coefficient is 1. So yeah, that was fine. And then we can go ahead and plug that into the calculator, and we get a concentration of 1,035. And that's the standard equation on how to calculate for the titrations. Most of them will be in this way. You can have a look in your textbook if you have something different. Go ahead and hit me up on Instagram, Facebook, TikTok, WhatsApp, so we can discuss how we can go over any examples you want, any help that you want in this area. Okay. Then we're going to move now to auto ionization of water. Okay. So we understand that water can act as an acid and can also act as a base. Nice. So it means that water can actually ionize itself. It can react with itself to form hydrogen. Now, the equilibrium constant, referred to as the ion product of water or the ionization product of water, for this reaction can be written as just the concentration of the hydronium multiplied by the concentration of the hydroxide. And at a temperature of 25, it is given as 1 times 10 to the power of minus 24. If you look in your formula sheet, you will also see that value over there. Now, at the temperature of 25, because water is in equilibrium with itself, we understand now that the rate of reaction going forward is equal to the rate of the reaction going backwards. The concentration of our hydronium will also be equal to the concentration of our hydroxide. But because they have a 1-to-1 relationship, and when you continuously make them and remove them and make them, so you're making them at the same rate, removing them at the same rate, therefore the concentration should be the same. So at 25 degrees Celsius, the concentration of your hydronium and your hydroxide would be 1 times 10 to the power of minus 7. This tells us that for a neutral solution, then the concentration of your hydronium and your hydroxide would be 1 times 10 to the power of minus 7. If your solution is acidic, it implies that the hydronium concentration should be greater than 1 times 10 to the power of minus 7. And if the solution is basic, then the concentration of your hydronium should be less than 1 times 10 to the power of minus 7. Now, the concentration of our hydronium and hydroxide are going to let us calculate the pH of the solution. So The pH of a solution is given by minus log the concentration of our hydronium, or in this case, our proton. We can also have a pHO, which is the pHO is just going to be the concentration of our hydroxide. Either way, our pH plus our pHO must give us a final answer of 14. And this is derived from the fact that Kw now, this is Kw at 25 degrees, is 1 times 10 to the power of minus 14, and it is the concentration of our acid or of our hydronium multiplied by the concentration of our hydroxide. The minus log of this would give us minus log of the concentration of our product multiplied by the concentration of our hydroxide and hydronium. Then we're gonna use log laws to separate those. And if you were to put the log, if we were then going to put the log of our pH, this will get a 14. So the pH of a neutral solution would be 7. The pH of an acidic solution should be greater than 7, and the pH of an acid should be less than 7. And the pH of a basic solution should, I think they mean basic here, should be then greater than 7. Okay. We can see that neutral atoms are found at 7. Basic solutions are found after 7. Alkaline solutions are found after 7, and acidics are found before 7. And they have given us real life examples of what is considered to be acidic and what is considered to be basic. Let us go ahead and look at calculating the pH of a solution. We're going to start with calculating the pH of a strong acid. Okay, so in this question here, it says hydrochloric acid solution has a concentration of 4 times 10 to the power of minus 3 mole per decimeter cubed, and this is at 25 degrees Celsius. They have given us the concentration of the hydrochloric acid. So the first thing we want to do is write down the equation that the hydrochloric acid is going to go through when it is in water to form hydronium and our negative ion. Then we will see that according to the recipe here, we have a 1-to-1 relationship between the hydrochloric acid and hydronium. We have a 1-to-1 relationship, meaning if we use 1 mole of hydrochloric acid, we have 1 mole of hydronium. Therefore, we can say that the concentration of your hydrochloric acid is equal to the concentration of your hydronium. Again, the reason being is that hydrochloric acid is a strong acid. So it means that it's going to ionize completely, meaning all of the hydrochloric acid that we put in water is going to ionize to actually form hydronium. That's why we can make also this basis that the concentration of our hydronium is equal to the concentration of our hydrochloric acid. Then, because this is at 25, we can use the Kw to say that the Kw is equal to the concentration of our hydronium multiplied by the concentration of our hydroxide. In this way, we are actually able to calculate the concentration of our hydroxide. If need be, we can calculate. But because we already had the concentration of our hydronium, we could have gone to just the stage over here where we calculated the pH using the concentration of our hydronium, and there's absolutely no problem with that. And we also have a way of calculating the pH for a solution from a strong base. So when you're calculating the pH, you can only do it with a strong base or a strong acid. The reason being is that they ionize or dissociate completely. So we know whatever concentration we have in our solution is going to be from those compounds. Here we have sodium hydroxide. Now, sodium hydroxide is a base, but it does not ionize in water. It dissociates. Ionizing is what we saw in the hydrochloric acid, where it actually reacts with water. Most bases don't react, they dissociate. The bases that will react is something like ammonia or sodium carbonate. So here we have sodium hydroxide dissociating in water to form sodium and to form hydroxide. Because we have a one-to-one relationship between the sodium hydroxide and the hydroxide, we can say that the concentration of the hydroxide is equal to the concentration of the hydronium. Now, method one would be for us to actually calculate the concentration of the hydronium. And once we find the concentration, so we will say that Kw is equal to the concentration of the ammonia multiplied by the concentration of the hydroxide. Therefore, the concentration of our ammonia would be equal to the Kw divided by the concentration of our hydroxide. And that is what we have over here. And we were able to calculate the concentration, and that was 1 times 10 to the power of minus 13. Now that we have the hydronium, we can just plug it into our equations for calculating the pH. Let's take a look at our formula sheet to see if the equation for the pH is there on your formula sheet. Then you can see the pH of this solution. You could use method 2, where you take the concentration of the hydroxide as it is, and you calculate the pOH instead of the pH. One thing we should know is the pH plus the pOH should always give us 14. So now that we know what the pOH is, we are able to calculate for the pH, which is equals to 13. That's the second method of how we can calculate the pH of a strong base. Okay, so for acids and bases are almost there. What we now need to look at is the properties that come with a weak acid and properties that come with weak base, strong acids, strong bases. So for a strong acid, we're going to say it's going to ionize completely. Therefore, it's going to have a very large Ki value, and the concentration of your hydronium will be equal to the concentration of the acid. And we're going to have a low pH somewhere around 1, 2, and 3. It would also have strong conducting abilities. Why? Because it's mostly going to be made up of ions, because it's ionized. So it is a strong electrolyte, implying that it can conduct electricity. When it comes to the rate of reaction, a strong acid would react faster than a weak acid. So then the opposite of everything we've learned here comes into play when it comes to weak acid. They ionize partially, therefore their Ka value is going to be low, and their concentration when you put them in water is going to be less than the original concentration, way less. Could be like 1% of what the actual concentration of the acid was. And it would have a higher pH value, so it would be somewhere around 5, 6, but not greater than 7. And it's going to be a weak electrolyte because it ionizes partially whenever we submerge it into water.